My name is Kamen Kozarev, and I'm a researcher at the Harvard-Smithsonian Center for Astrophysics. What are the energy spectra that are produced in these acceleration processes? On the right side of this slide, you can see a nice plot that shows you the energy spectrum of all the plasma that was observed during an energetic storm particle event. In other words, an energetic particle eruption. On the y-axis, you have the distribution function, which is another word for density of the particles, okay, or the intensity of the particles. And on the right side, on the horizontal axis, you have the energy in kilo electron volts. In the lowest energy regions, you have the solar wind protons. In other words, you have the lowest energy particles, those particles that are moving constantly, streaming out from the sun at about 400 kilometers per second, between 400 and 800 kilometers per second. And this shows you a little bump. So it's basically a distribution that has a peak and then it declines when you go to higher or lower energies. And this is always there. It basically doesn't change. It changes a little bit with the solar cycle, but not by much. Then when we go higher in energy, you have the so-called solar wind alphas, which are the helium nuclei that have a little bit higher energy. After that, you have the energetic particles that are released in this single event, which form a spectrum that's not such a distribution with a peak and dips, but it's a power law spectrum. So you can see on this log-log plot that it's a straight line with a certain slope. The other thing that can be observed is that around a few hundred kilo electron volts you have a break in the spectrum, which may be caused by different acceleration mechanisms, or by the fact that these events are finite in time. In other words, it takes a long time to produce this power law spectrum. And if you haven't had enough time, then you have this break. In other words, the intensities of the particles will drop significantly at the high energies. If we talk about the particles at the shock, at the low energies up to several hundred kilo electron volts, all the three different acceleration mechanisms can be observed. You can have diffusive shock acceleration, shock drift acceleration, and stochastic acceleration. And these little drawings show you the magnetic field interaction with the shock surface. And on the bottom, it shows you the corresponding observations, in other words, the intensities over time that are observed. So the spectra and the upstream increases are in agreement with predictions from the models. These three mechanisms can be actually observed. When we go to higher energies, it gets very interesting because these particles are not confined to the shock region. In other words, they get accelerated and then they leave. So in that case, it's the transport effects that are more dominant. But it's also very hard to tell what caused the acceleration or where it happened, because these particles, as I said, tend to leave the acceleration region very quickly. So the profiles that we observe as a single spacecraft of these particles can change depending on the location of the spacecraft relative to the source of the eruption, relative to the shock wave longitude. And here you see four different examples of how, for a single event, the particle distributions over time that were observed can vary significantly, simply based on the position of the spacecraft relative to the source on the sun. And so that makes the interpretation of the observations extremely difficult, and one has to be very careful to include all the different effects and also the realistic geometries of the magnetic field, of the plasma, and the shock wave that is produced. What we have ultimately is that the predictions from theory, as we have them right now, are not always in agreement with the observations. And the possible reasons for that is that there is the convolution of the acceleration and injection and the subsequent propagation. In other words, you have to consider not only the injection, the location, the amount of acceleration, but also the transport in time. Everything is convolved together. You may also have incorrect application of the model. For example, when you don't wait for the model to reach a steady state to apply it, you may have additional acceleration mechanisms that have not been discovered or included in the models. And also you can have acceleration not from the solar wind, which is where the sources of these particles come from, the seed particles that are accelerated, but you can have acceleration of particles that are left over from a previous eruption. So all these things make the agreement to the models very sketchy at best. To sum it up, the acceleration of particles in the high energy ranges is not really fully understood. Another problem you may have is you can have several shocks. There's nothing stopping the sun from erupting several times. You can have several flares, you can have several shocks that can converge. In other words, they can get close to each other over time. And in fact, extremely large particle events are often observed to occur between two eruptions or two shock waves. For example, you can see these observations on the right here that show you two shocks that reach the Earth, and you can see the significant increase of the particle fluxes between the two shocks, but then outside of them you don't have a great intensity of these particles. This is mostly caused by efficient acceleration by the diffusive shock acceleration mechanism. So what this means is that the properties of these events correspond and depend on not only the sources and the seed particles, but also on the properties of the interplanetary medium, which changes all the time. For example, here you can see some eruptions that were observed by a coronagraph, which is a telescope that blocks out the sun itself, but allows us to see the fainter corona, the faint atmosphere around the surface of the sun. And so what you can see is that you can have multiple CMEs short amount of time that can interact and can change significantly the distributions, the profile of the energetic particles. Now let's talk briefly about particles at co-rotating interaction regions. The shocks that can form at these can accelerate particles to high energies, high enough energies, several mega electron volts. So let's compare them with coronal mass ejection driven shocks. On the right you can see a nice comparison with bullets. First of all, the CME driven shocks can accelerate particles to much higher energies, about 10 times as high, up to 100, maybe several hundred mega electron volts, while the shocks accelerating particles near co-rotating interaction regions can only reach up to 10 mega electron volts, which is much smaller. At the CME driven shocks, the particles tend to stream away from the shock, further upstream towards the Earth, let's say, while at co-rotating interaction region shocks, particles tend to stream towards the sun. The acceleration efficiency also varies between the two types of shocks. The CME driven shock acceleration is best or most efficient near the sun or up to 1 astronomical unit up to the Earth, while co-rotating interaction regions tend to accelerate particles most efficiently farther out, close to 4 astronomical units. There are some other differences that pertain to, for example, the composition of the particles. Here you can see how the particle intensities change as the co-rotating interaction regions pass by the Earth. There are some very specific signatures in the plasma that can tell you that there's a CIR passing by the Earth or by your spacecraft. You can have a change in the azimuthal angle of the magnetic field, a change in the solar wind speed, since it's an interaction region. But on the bottom, you can see how the particle fluxes change as it passes by. And you can see that for the low energies, up to about 6 MeV, you can have increase based on the passage of these CIRs, which is indicative of acceleration very close to these CIR fronts. Finally, we'll talk about the particles at the bow shock and how they may get accelerated. The acceleration can reach only very low energies. In other words, these are not very efficient accelerators, since the difference in the speeds is not very great. On the right here, you can see a schematic of the interaction of the solar wind with the Earth's magnetopause and the bow shock. This is looking down on the Earth and the magnetosphere. The arrows are the magnetic field, which makes an angle of approximately 45 degrees to the line between the Earth and the Sun. So what happens is you have different types of shock based on the angle between the shock surface and the magnetic field. You can have a perpendicular type shock where the magnetic field is perpendicular to the normal to the surface of the shock, or you can have a parallel shock. And so in this case, on the left side you have a so-called quasi-perpendicular shock, while on the right side you have a quasi-parallel shock. When you have a quasi-perpendicular shock, you may have more acceleration from the shock drift acceleration mechanism, while when you have a quasi-parallel shock, you can have more diffusive shock acceleration. So the mechanism itself might vary along the surface of the shock, which makes it, of course, much more complicated. Galactic cosmic rays, finally, the last type of particles, they tend to stream into the solar system from every direction, basically. So imagine how the sun is part of the galaxy, and now imagine that there are stars exploding all around us in every possible direction. That can be an explosion of a supernova somewhere far away in the galaxy, which will accelerate these particles to extremely high energies. And when that happens, they tend to leave that star's local environment, and they start meandering throughout the galaxy. During that's also a transport process, and so you can have interactions with magnetic fields, irregularities, and so on between these particles and the environment of the galaxy. Of course, they have much higher energies, so their interactions occur over much larger distances. But eventually, they might get into the solar system. And because these explosions happen everywhere, the source is pretty isotropic. In other words, from any side of the solar system, you can expect to have approximately the same intensities of these so-called GCRs, galactic cosmic rays. The composition of the galactic cosmic rays is mainly electrons, protons, and alpha particles, with much smaller contribution of all kinds of heavy nuclei up to iron. Why do they only go up to iron? It's because those are the elements that are created in the generation of energy in the cores of stars. And they have an approximate flux at Earth of about 1,000 particles per square meter. What's interesting about galactic cosmic rays is that they are modulated by the solar cycle. The amount of activity of the sun changes every 11 years. There's a cycle. With that, what changes is the magnetic field that the sun releases in the solar system. Since these particles, galactic cosmic rays, interact with magnetic fields, they're themselves ionized, they can be modulated, they can be deflected by the increased amounts of the magnetic field in the solar system. And that's why, for example, we saw that anti-correlation between the high energy fluxes and the sunspots on the sun. Whenever you have large numbers of sunspots, you have more magnetic field in the solar system, and therefore you have lower fluxes of galactic cosmic rays that can be observed, and vice versa. This is a spectrum of the GCRs for different types of particles. You have hydrogen, helium, carbon, oxygen, nuclei, and ion. You can see here on the y-axis, again, the particles per square meter, and on the x-axis, you have the energy, which is here quoted in giga-electron volts per nucleon. For the higher energies, you can see a straight line, in other words, a power law spectrum. And on the left, they get mixed up with, there's a peak, and then to the left of that, they start falling down when they get mixed with the local energetic particle populations. What's interesting to observe here is that these particles continue from the SEP part of the spectrum out up to 10 to the 20th electron volts. As I mentioned, the modulation of GCRs is readily observed. That happens to particles with energies below a few giga-electron volts, since they can actually sense the magnetic field. Particles with larger energies don't really see the changes in the magnetic field, since their mean free path for interaction with other particles is much larger. It's as large as the solar system or even bigger. So they don't really see the change of the magnetic field with the solar cycle. But for the lower energy particles, you can have this modulation that can be seen here in this plot. On the y-axis, you have the smooth monthly average count rates of neutrons, which are particles produced when GCRs interact with the Earth's atmosphere, so they correlate with GCRs. And on the x-axis, you can see time in years. The solar cycles are numbered, and you can see the successive dips and peaks in the GCR counts. One interesting thing is that there's a time lag between the GCR variation and the variation of the sunspots, which is caused by the fact that it takes time for the magnetic fields to be released all the way out to 100 astronomical units, where the heliosphere. There are different types of modulation models for GCRs, and they're based on the magnetic field that the sun releases, as I mentioned. They can switch as the sun switches magnetic field. The location from where you have most GCRs coming into the solar system can change, and they're usually most of them come from the polar regions, but then they spread out close to the solar equator. And GCRs and their modulation is also governed by the same transport equations that we mentioned previously. They can be diffused in space, they can be convected, and they can move in bulk, in other words, their own motion. And of course, they can interact with the magnetic fields. When they reach the atmosphere, many of them, because it's very hard to stop these extremely energetic particles, they usually interact with the ions and neutrals high up in the atmosphere. They cause ionization above the mesosphere, but there isn't much interaction until they reach lower into the atmosphere, where they can deposit their energies, and they can cause a cascade and creation of secondary particles and neutrons that are observed then by these neutron monitors. Something very interesting about GCRs is that their increased numbers may cause an increase in cloud coverage. In other words, they can act as sources of cloud droplets. Basically, rain droplets can form around secondary particles which are formed when these GCRs interact with the atmosphere. I personally find this amazing because it means that some particles produced thousands and thousands of light years away from the sun can actually influence weather patterns on the Earth. So, to summarize, energetic particles in the heliosphere have many different sources, different composition. They have different energy spectra, temporal variation. They're produced in different processes. The acceleration of these particles, the energization, may be due to reconnection when this happens usually very close to the sun in so-called flare eruptions. But it can also happen in shock waves near the sun, near planetary environments, or even further out towards the edge of the solar system. This leads, however, because we have so few observations, to many open questions about the processes of acceleration. As I said, we don't have an extremely good agreement between our models, the physical models, and the observations. And so it's a very interesting discipline because there are very frequent changes in the paradigm, in the framework of our understanding of these energetic particles. The particle propagation itself is determined by different types of scattering, pitch angle, diffusion in space, diffusion in momentum and energy, and the large-scale magnetic field, which governs all the transport processes in the heliosphere.